Hello everyone, welcome back to my channel. Today I am going to explain a recent paper which is published in Archive called Relaxing the Conditional Independence Assumption of CTC-based ASR by Conditioning on the Intermediate Predictions. This paper is a collaboration between Line Corporation from Japan and Kyoto University. These are the authors. So the overview is like this. We are going to first see the introduction of this paper, basically the abstract of the paper. Then we'll see what is the proposed approach, and then we'll see the experiments results. And also I'm going to share my thoughts on the implementation of this paper. So the code base is not available, so I tried to implement this paper on my own, and I'm going to tell you like what are the insights and what are the difficulties I faced during training. So the idea of this paper is very simple. In many speech recognition applications these days, or speech recognition algorithms people publish these days, mostly there are two objective functions people use, at least in end-to-end speech recognition models. So the objective functions people use are CTC loss and another loss which usually people call it as attention loss, but this is something like a cross entropy loss in sequence to sequence modeling, right? And these are the two mostly used loss functions for end-to-end speech recognition, and there are other loss functions like end-to-end LFMMI and other things which you can also use, which are which actually comes from the discriminative training objectives for speech recognition, which were developed back in 2005 and 6. And the biggest problem with CTC loss, we may not be able to call it as a disadvantage or problem. The way the CTC loss works is it assumes, or it has something called conditional independent assumption. So what is that conditional independence assumption is, I'm going to explain to you in the coming slide. But in a simple way, we can understand it as when you are predicting something at some time step, you are not going to look at previous time steps output or the past time steps output. Right? So the condition, this conditional independence assumption basically assumes, so the output, the current output condition, it's independent of all other outputs. It could be a previous outputs or could be the future outputs, right? So that is the conditional independence assumption, and obviously we want to in case of speech, since there is a lot of dependency between the previous frames and the future frames, you may want to add that dependencies assumption or Markov assumption into this loss so that you get better results, right? So that is the idea of this paper. So the idea of this paper is relaxing the conditional independence assumption of CTC loss for a speech recognition model. And how do you do that? So that's the theme of the idea of this paper, and we will understand how that is done in the coming slides. And as I said, so that is done using something called auxiliary intermediate losses, or auxiliary CTC losses computed in the intermediate layers and added to the final loss. And this is somehow going to add the conditional or relax the conditional independence assumption and makes the frames dependent on each other. So we will see that in the main proposed approach section. And this approach gives a significant improvement in WR, and they get 20% relative improvement on WSJ corpus, and also they get improvements on Deadlium corpus and ASL corpus. So coming to the proposed approach section, we are going to explain it in three different parts. First, I'm going to explain to you what is connectionist temporal classification for speech recognition. I think many people must have already, if you are working in speech or even in image, you will be knowing about connection is temporal classification loss function, but I'm going to explain it anyway once. And we are going to see how transformer encoders can be used for speech recognition using CTC loss. And most of the time when you see transformer papers for speech recognition, usually they will be in the in sequence to sequence fashion. There will be an transformer encoder and there will be a transformer decoder. So and the output of the transformer decoder will go as input to the encoder will go as input to the transformer decoder, and then you will be able to predict sequence of characters or sequence of sentence subwords in autoregressive manner, right? This is the same idea borrowed from neural machine translation applications, and but in this case we are going to look at a simple transformer encoder, which is going to take audio, or it could be some spectrogram or Mel spectrogram as input, and this transformer is going to take this as input and going to give you sequence of predictions, and these predictions can be used as input to the CTC loss, and you can compute the CTC loss. So this is the idea of this paper. So there is no decoder or anything, it's just a simple encoder and then CTC layer. And in this paper they want to sorry about that, in this paper they want to use this relaxing assumption for CTC, and how are they going to do that, and we are going to explain it in the 2.3 section. So what is connection is temporal classification, also known as CTC. So the CTC is a loss function, and it looks like this. And there are multiple parts you want to understand in this. So there is a sum, this part, and there is a logarithm, and then there is this term. And this term can be expanded as this. And this term is nothing but the probability of the output given the input. And x here is a spectrogram. And the idea of this paper, or the idea of this CTC, is to take this x, the features, and predict, or features is in this case could be a spectrogram, right? So what is the output condition on x? X is basically the input audio, and a could be a sequence of characters. Like for example, if you say hello, it is sequence of characters, but not exactly a sequence of characters. You want to do something called a mapping, or mapping, which is basically making the length of this output similar to the length of the input. And so the what I mean by that is x is nothing but a spectrogram, and spectrogram is nothing but sequence of frames, right? So sequence of frames, if your audio is, let's say, 1 second, and if you compute features for every 25 millisecond window with 10 millisecond shift, you are going to get 100 frames, right? And when I say length of the spectrogram, I mean L is equal to 100, because you have 100 frames, right? But the input length may not always be same as the output length. So the output length here is basically the the length of the character sequence, right, or length of the sentence. And this sentence could be a simple hello, right? It has only 5 letters or 6 letters, right? And this length is not same as this, so somehow we want to make the length of this same as this. So for that we use something called mapping. So this mapping here, basically what it does is it repeats it. There are 3 rules which you can apply to make these two lengths same. So basically you can repeat the characters, or you can pad with some unknown tokens, or extra symbols, underscores or some other symbols, and that way you can make these two lengths same, right? So that is this a, that is what is called a. So after you map it, then you get a, and there can be multiple ways you can do the padding and repetition, right? So that's why it's coming from the space of possible uh, sequences, all possible sequences. And this a basically will have length, let's say s, right? The product goes from s equal to 1 to s, and as you can clearly see here, so the probability of as could be a simple character sequence at s time step, and it's conditioned only on the input, but it is not conditioned on any other outputs, right? So this is so this from this you can clearly understand there is conditional independence assumption going on here, because the output clearly depends only on the input but nothing else. In case of Markov assumption, or in case of autoregressive assumption, if you see the autoregressive way of predicting the outputs, if you, when you have encoder decoder architecture, so the output at the current time step t depends on the current time step input and the previous time steps output, right? So there is a Markovian assumption there, but in this case it is not. So there is it's good to have the Markovian assumption, because you will be able to see what is the previous output, and you can improve your predictions in the current time step or in the future time steps when you know what happened in the previous time steps. And there is this assumption, actually it's a good assumption for speech, because the speech is a temporal signal, and it's a dynamically changing signal, so it's always better to have, or better to know, the previous time steps output, right? So so I hope you guys understood what is CTC. So when you can compute this, you can just plug it here, then you compute the sum and use the log for some numerical advantages and so on, and then you get this CTC loss, right? So then everything remains as it is. You just train the model. uh, so how do you train the model? So in this case they are using something called transformer encoder for CTC loss. So this transformer encoder it's a simple transformer architecture, could be 10 layer or 20 layer architecture. So what happens is let's just get some equations into your mind. So when you are looking at uh, the L plus 1th layer, so the L plus 1th layer basically takes the output of the Lth layer as input, right? And what what the what we are going to do is we take the output of the last time steps, and of the last layer, sorry, and then we do apply layer normalization, and then the output of the layer normalization will go to the linear layer. So the linear layer basically changes the dimension of dimension from D to V. So V here is the vocabulary, and this vocabulary could be 32 in case of English if you are doing character based predictions. This vocabulary, once you convert this into vocabulary, then you can simply apply a softmax, and this ZL can be used as input to the CTC loss, right? And you compute the CTC loss and train the model into it, as simple as that, right? And these are some of the equations you want to know, because since you are using transformer, what happens inside transformer is you have simple self-attention layer or multi-head self-attention layer, and then you have fully or feed forward network, right? So XLN is the input from the Lth layer, and you just compute you just calculate the self attention for that input, then you add it to the original input, and then you have fully feed forward, and then just sum, right? So this is very simple, right? So transformer and then CTC. Hope you guys understood. Now let's look at the proposed architecture. So whatever I explained in previously, the CTC loss and the transformer architecture, which is what you can use if you are building a simple speech recognition model for some data set, right? And you don't have to worry about anything. It's just those two equations, or one architecture and one loss, and everything will work fine. But how are we going to relax the conditional independence assumption of the CTC? So we can do it in this way. There are multiple other papers which are also published in the same area. So because it's one of the very well known problem, right? So there is a paper called CTC, there is a mass CTC, and so on. You can read about them. Those are also a recently published paper, and this paper actually shows the numbers on those papers also, like what is the accuracy with those papers, or with those models, and what is the accuracy with this model. So we'll see those numbers in the result section. Let's understand what is the idea of this paper, right? So the proposed architecture looks like this. So assume you have speech, your speech gets converted into spectrogram, for example, right? And you have the spectrogram X, and this X goes as input to the transformer, right? So the transformer is again n layer or n layer transformer. So n could be 20 or 30. In this case, they are taking 18. What is going to happen is so the one layer of this transformer looks like this. So you have a layer normalization, then self attention, then layer normalization, feed forward. This is one layer of one transformer encoder. So let's call it as TRM encoder layer, right? So this is one layer. Now the output of this layer, we are going to add some other new block in the middle. Let's look at this block in particular. So this new block, what we are going to do is, we are going to take the output of feed forward of, let's say, layer 3 and give it to a layer normalization layer, and then we give it to a linear layer. So the linear layer converts a dimension d to v, because you want to apply softmax, and softmax can be applied over sequence of character labels, and you want the vocabulary v, right? So this linear layer converts the dimension d to v, then you apply softmax, and then you give it a CTC loss, right, at the third layer, right? And you do the same thing at sixth layer or ninth layer, 12th layer, 15th layer, and 18th layer, right? Now the question is, okay, we can compute the loss, and we can just add all those loss and train it end to end. But how is it going to change, or how is it going to uh, relax the conditional independence assumption? So the way that you do is, once you get that softmax output, you take the softmax output and give it to another linear layer, which is going to convert the dimension or which is going to convert uh, the uh, the dimension v to d again, right? It's a kind of a reverse linear layer, and then you add that output to the layer normalization output, and then feed it to the next layer, right? Now here you can see two things. One is, you are taking this loss anyway, this is loss from third layer, and that's going to affect the output at this layer, and output at sixth layer, ninth layer, and so on, right? So you are basically conditioning different losses at different layers, and they are all CTC losses, losses at different layers. So that way you are kind of adding the intermediate representations, or learning intermediate representations, which looks at the loss at the final layer, right? So this is something new, which these people have proposed. So I hope you guys understood like how this thing is working. So you take every third layer, you take the output and give it to this block basically does all this magic, and then adds it back to the layer. And then, so once you get once you pass through the full network, you just add all the losses. So it goes like this, very simple. So the L plus 1th layer input is basically layer normalization, and you're going to add this is the add symbol, add it to this linear v to d of zl. So the zl comes from here, and linear is this linear, and converts v dimension to d dimension, and these two dimensions will be same. Once they do that, then you can simply add them, right? And do the same thing for all for every 3 layer. So if you have 18 layer, you get 5 CTC loss, and you just add all those losses like this, add all the losses, compute the mean, and then you add it to the original loss, which is the main CTC loss, and you add it with some scalar, right? This is how it works. I hope you guys understood. It's very simple. Now we'll look at the experiments. Experiments are conducted on 3 different data sets. One is Wall Street Journal, which is of 81 hours, and there is a Tedlium 200 hours of data, and then AI Shell 1, which is of 170 hours of data. And 80-dimensional log mill spectrum features are used, along with 3-dimensional pitch features. Also, spec augment is used for data augmentation, right? And speed perturbation is also used for data augmentation for Tedlium and ASL, and 50 characters for WSJ, 50 characters is the vocabulary, 500 subwords for sentence fees for Tedlium, and 4231 characters for ASL. ASL is a Chinese audio corpus, and as you know, Chinese characters or words are I mean, there are more number of characters in Chinese language. That's why there is 4,000 characters. I mean, I think there are more, but they are only taking those important ones, are the ones which are used every day. And coming to the model section, you have 12 layer encoder, not exactly 12 layer encoder. So basically, they are just taking the implementation from ESP.NET, which uses in standard, uses these ones, but they are using 12 layer, 18 layer CTC 18 layer encoder with to match the encoder decoder or autoregressive models parameters, and then they train it for 100 epochs for the Wall Street journals and 50 epochs for Ted Liam, and they are going to average 10 checkpoints with which has good validation scores, the top validation losses, and batch size is 128 and so on. Now let's look at the results. Obviously, you can see the best model is this proposed approach. So as I mentioned, the inter-CTC is one paper which is published in this year, ICASP by Shinji Watanabe from GHU and another guy from Naval Corporation Japan, I think, and that paper is this inter-CTC, which also works really well, and it's a good idea. I mean, if you're interested in this area, you should look at it. And these are some of the benchmark numbers. If you just use autoregressive, which is the standard out of the box Kaldi or ASP.NET recipe, you get the best system if you use autoregressive. But in case of I mean, obviously autoregressive works really better, right? Because inherently you have this dependency assumption. But in case of CTC, you don't have it, but the speed in CTC will be faster because you don't have to do autoregressive prediction for every time step, right? So that is these autoregressive models are slower compared to non-autoregressive models, which are CTC-based models, right? And as you can see, there is a real-time factor which is really good for non-autoregressive models, and sometimes and obviously the best models are autoregressive ones. But in case if you compare, if you are interested in real-time factor, the speed and the accuracy, I think you can use these non-autoregressive systems. That is for the OSHA journal, and for AI shell, same thing applies here, but in this case they are almost able to reach the autoregressive numbers, as you can see here, and in the case of test, it is actually getting a little bit improvement on autoregressive autoregressive models, and obviously the RTF is really good compared to autoregressive models. This is one model where you can see the effect of K. K basically is the number of layers you are choosing to compute the CTC loss. When I say K is 3, then you are taking let's say every fifth layer for the to calculate the intermediate CTC loss, right? And when I say in case of when I say 5, it's basically you're taking every third layer. When I say 17, you're taking all the layers except the first one, probably, right? So this is as you can see clearly, the uh, the proposed approach gets the best accuracy, which is this dark blue. Inter-CTC is another approach which I told you about from Shinji Watanabe and another guy, and the CTC, just CTC using the normal CTC output gives you the worst WR, and same thing applies for almost all the Ks with different number of layers and so on, right? And yeah, I think that's about for this tutorial. So basically, so just to recap, so the paper basically talks about how do you relax the conditional independence assumption in the CTC frameworks or in CTC speech recognition models, and how do you make them as close to autoregressive models without losing the speed. And so this paper basically gives the idea of using intermediate loss of computing intermediate losses, and so that way you can condition on the intermediate representations, which in turn gives you improvements on the state of the art state of the art accuracies for WSG and Tedlium and ASL corpus. And that's all for this tutorial. Thank you so much for watching this tutorial. Please subscribe to my channel if you want to get notifications for these kind of content. Thank you.